talking about chemical bonds. And my question is, do you remember the two types of bonds? There's covalent and ionic. Nicely done. Covalent and ionic. Do you remember the difference between these two things? I know you covered this in 8th grade, I know, only because my son just started it last year. What do you think?
Ionic is like when there are two different charges and they attract to that.
Mm-hmm.
Covalent is they share.
Absolutely. Sharing is covalent. They're sharing electrons. Sharing is carrying. And ionics are where they take. One takes and one gives. So we're going to talk about ionic compounds. So let's briefly, well, before we go to that. As an example, Joshua has these lovely Kleenexes here, right? We're going to use the Kleenexes to represent the electrons that Joshua has. He only has one valence electron. So what group element would he be in with one valence electron? He'd be in group 1, right? Group 1 has only one valence electron. Okay? So I come along and I am a group 17 electron, or element. So how many valence electrons do I have?
7.
I got 7, right? What's the magic number? 8. There's something called the octet rule, right? The octet rule says if you got 8 electrons in your outermost level, oh, you are happy. Okay? So I come along and I steal Josh's Kleenexes, his electron, right? So how many electrons do I have now? I got 8. Am I happy? I am happy. How is Josh doing? He's happy?
No.
Why is he happy? Because he is happy. He's very excited that I took his electron. He got rid of one extra, but wait, doesn't that leave him with no electrons then?
Yes.
Oh, remember there's levels beneath his valence electrons, right? Are you with me? Valence just mean the outermost electrons. So underneath that one electron, Josh has a whole level that now is the outermost, and now it's full. And so Josh is happy. He's got his octet rule, like a noble gas. I'm happy because I took that extra one, and I'm happy. So us hanging out together, us forming a chemical bond, makes us both happy. Are you with me?
What about two that are trying to take?
Oh, well, they wouldn't react. Yeah, if you were trying to take, and he was, and we're both trying to take from Josh, we would not react because I'm trying to take you. We can't.
What if you were trying to take one and Josh wanted to take one?
It wouldn't work. We wouldn't bond. Yeah, it's only if he's got ones to give, or frankly, if I'm stronger, if I'm more impressive, I can take it.
Like your noble gas or something?
Nah, we'll talk more about which ones
Not
are like
noble
that.
gas, but the alkali.
Right. Group 17 would be the ones who could take the most. We'll talk. We'll show you. Okay? Are y'all with me?
Yes.
This is a chemical bond. This is what we're doing. Yes? Oh, that's a great question. Do they change elements if you take electrons? What is it that makes an element an element? It's the number of what? Not neutrons. Not electrons. Protons. And the number of protons stays the same. So no, I am still the same element I was when I took that electron. And you're the same element as you were if you lost it. We just have a charge now. What do we call an element that has a charge? It's an ion. It's an ion. Are you with me, friends? All right. So here we go. Chemical bond. How would you define this? We're over there on page 206 in 7.1. Yes, ma'am. Use the force, Luke. Force that does what? Holds, and I put 2 in parentheses, or more atoms together. All right? And we were just talking about those 2 different kinds, ionic, covalent. We are talking about ionic today. That's what we'll spend our class period today discussing. Okay? Now, when Josh and I are reacting, right? We're forming a bond. I stole his electron, right? He lost his electron. Okay? Are you comfortable that then there's a positive and a negative ion here? One of us is positive, one of us is negative. Cool? One of the names of those is what we call a cation. What is a cation? That's a positive.
Two words or one?
It's one word. Okay? Yep. Mm-hmm. Right, there is no dog. This is strange, but right. Okay? So let me ask you this. In Josh and I's example here, which of us is the cation?
Josh.
No, you are.
Josh is.
Maybe there's some. Okay, let's talk about this. Let's see if we can vote here. Now listen, hang on. Shh, 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 shh. I want you to think. Okay? Are you comfortable that this Kleenex box is representing what? Electron. Okay? And I have taken this electron from him. Right? So he's lost an electron. I've gained an electron. We cool? Okay? Cation is what charge? Positive. Okay. So with a raised hand, which of you thinks that Josh is the cation? Got a couple. Okay, hands down. Which of you think that I am the cation? Couple. Okay, good. Let me ask you this. What do we say this Kleenex box represents?
Electrons.
Electrons. So what charge are electrons?
Negative.
They're negative. Are you comfortable that I have now added a negative charge to me? And Josh has lost a negative charge. So do you think he's positive or negative? Or let me ask you this. Am I positive or am I negative? I've taken a negative, right? So therefore, what must he be? He's positive. Because remember, atoms have the same number of protons and electrons, right? So if Josh gives me, if I steal one of his electrons, he still has the same number of protons, right? So therefore, he must be positive. Are you with me? Yep. So Josh is a cation. He is a positive charge. He has lost electrons, right? Now, let me ask you this. Based upon what you know about our electron configurations, what we did in this last unit, is Josh a metal or is he a non-metal? Don't answer out loud. Is Josh a metal or is he a non-metal? Think about the configurations. I told you that Josh was a group 1, right? With his 1 valence electron, right? And I said that I was a group 17 with my 7 valence electrons. So which do you think? Is Josh a metal or is he a non-metal as a cation? How many of you think that he is a non-metal? Raise your hands. How many of you think he's a metal? And some of you just aren't sure. Okay. Which one of these is going to lose an electron? Group 1 or group 17? Group 1 is going to lose an electron, right? So it's going to be a positive charge, right? So therefore, what are group 1s? They are metals. They confuse you with that stupid hydrogen up there, doesn't it? Hydrogen is like its own little thing. It's funky. Some periodic tables don't even color it the same color as the nonmetals because it's so funky. Because it only has 1 proton and one electron, right? So if it gives away that 1 electron, it has no more. There's no under levels. You with me? So it won't do that. It shares, is all hydrogen usually does. It doesn't, because then it would have none. Does that make sense? It usually shares. Okay, so therefore a cation is a positive charge. You've lost electrons, and it is a metal. All of the metals on this periodic table, which is the vast majority, right?
Does it have to be metal?
To lose it, metalloids are the only ones that can go both ways. We'll talk about those. But yeah, metals are the ones that lose electrons, that form cations, that give you a positive charge. Are we cool? All right, let's take a look at some of these things. Okay? Let's take cesium as our first one. Can you give me the shorthand electron configuration for cesium? You have to use your periodic table. This is in the back of your textbook. Cesium is way down the left corner, number 55. Shorthand, electron configuration. Xenon, 6s1. Only one electron in that 6s, right? So let me ask you this. How many valence electrons does cesium have? It's got one, right? Okay. So if it loses its electrons to become like a noble gas, right? What charge will cesium have? Positive how many? Positive 1. Does that make sense? It wants to get rid of this one electron so that it can just be like xenon. Right, because remember, xenon here already has full, the 5s, the 4d, the 5p is already full, right? So it's happy. So if it gets rid of that one extra electron, then he's cool. He's happy. Does that make sense? If you give away this negative, and it seems crazy, right? You're giving away something, so you're positive? What? It just seems odd. But remember, the electrons are negative. Yes, ma'am? It doesn't. Why does it not become a different element? The protons stay the same. Remember, the protons are what make it what it is, not the electrons. It becomes an ion because it now has a charge, but it's still cesium. Good question.
Sorry.
It's okay.
So what if you got, I'm not sure if this is the question I asked earlier. What if you got 2 from the first
Period. Or group. They would not react
at all?
at all.
None of them react.
They would not. They would form a mixture, right? They can make an alloy. 2 metals together make an alloy, but there's no chemical bond that's formed between them. They can just be in the same place together, but there's no chemical bond. Okay? Let's talk about barium now. Next one over. What would its electron configuration be? Shorthand. Xenon 6s. We're going to fill up that 6s with 2 electrons. You cool? Yep. So if this thing reacts, if it wants to get rid of those electrons, to be stable, to be a noble gas configuration, what would its charge be? Excuse me, +2. You got it. It's going to give away both of these electrons. Excuse me, got the hiccups. Does it make sense? Okay. Now let's do thallium. Thallium's over here in group 13, number 81. So let's do shorthand configuration for thallium. Xenon 6s2. Oh, you remember. Nicely done. 4f14. 5d10. P1. You got it. Because it's over here in group 13. Okay. Whew, I'm impressed. I thought you were going to forget about those F's and D's. So nicely done. Now, I ask you, how many valence electrons does thallium have?
3.
You say 3. How do you know? Give me a raised hand. How do you know?
Because now its electrons is made up of the S&P.
The outermost. Yep. Sir?
It's because you have to look for the highest number. And 6 would be the highest. So that's the outer row.
Sure, because 4 and 5, those levels are all full, right? The S and the P's were filled up with xenon. Okay? From the outermost. Exactly. And remember we said that group 13, you know it has 3 because you just cut off the 1, and it has 3. Right? So therefore, which of these are my valence electrons here?
6s2.
6s2 and
1.
6p1. Those are my valence electrons, right? So if I give away those electrons, what charge will this lovely thallium have?
+3.
+3.
Wait, so if it was like 6s4 or 6p4?
We'll talk about those. At this point, this is where we'll stop at group 13. Because groups, group 1, group 2, group 13, you know they'll have this charge based upon their number of valence electrons. Are you with me? They have 1 extra, they have 2 extra, they have 3 extra. They're going to give those away to be happy. And we'll talk about the other ones in a second here. Make sense? All right. So again, we said, as far as Josh and I in our example, Josh was what? What do we call him? A cation, right? He gave away electrons, so he became positive, right? Excuse me 1 second. We cool? So Josh was a cation. The next thing is what we call an anion. Not a dog ion. It should be a dog ion, shouldn't it? But cats and dogs, they don't get together, they fight. Whereas these guys want to come together, so that wouldn't work. Okay? So what do you think an anion is then? Some of the negative charge. So do you think it gains electrons or gives away electrons? It gains them. It takes them. Yes. Takes, not negative. It takes electrons. And what kind of element do you think this is? Metal or non-metal?
Non-metal.
These are our non-metals. Are you comfortable that an ionic compound is always a metal and a non-metal put together? That is what makes an ionic compound. Because you want a cation and an anion together. We want a positive and a negative together. And that makes a neutral. That's exactly right. That's the whole point. The only reason that Josh and I are happy with me stealing his electron, his box of Kleenexes here, is because it makes us both happy. It makes us, I get 8, he gets 8. He's positive 1, I'm negative 1. We're happy. Absolutely, win-win. We would both have to have a charge, and then together our compound is neutral. The two of us together make a neutral. Yes, we form a chemical bond. We form an ionic bond. Yes, sir. Yep, I'm taking his electrons. He is giving them away. He's a metal, I'm a non-metal. Yes, sir. We cool? Maybe. Let's do some more here. Because positive and negative attract, right? Right. Because we're happy. I've got 8, he's got 8, we're both happy. Whereas when we were apart, he had 1 extra and I was missing 1. So the two of us together make us both happy. Did I get you? We were just stretching. Good. All right. So let's do some more configurations. Let's look at some non-metals now. Chlorine. Can you tell me, please, what is the shorthand electron configuration for my friend chlorine? It's number 17. So neon?
3s2.
3s2? 5. Good. Okay. How many valence electrons? He's got 7. 7 valence electrons, right? What's the magic number? 8 is the magic number. So here's your question. Is it easier for chlorine to lose 7 or to gain 1? Doesn't that just make sense? It's just easier, right? And remember, electrons, everything's lazy. Whatever takes the easiest amount of energy, the least amount. Okay? So he's going to add 1 more electron to get to that magic 8 number, that octet rule. Okay? So therefore, what will the charge be of this chlorine? -1. And you say, wait, hold on. But he added an electron. Why is he negative?
Because he's a negative.
Electrons are negative.
How can you tell if it's an anion or a cation?
It's a non-metal versus a metal.
So if it's non-metal, then you always add it.
Yes. Metal, you give it, exactly. Sir. Shh, 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 shh. What's that? Right? So I can either, as chlorine, I could give away all 7 of my valence electrons and become a +7, or I could take 1 more electron on and become a -1. And that's just easier. It's less energy for me to take that 1 electron than it is to give away all 7. It is possible. You could make it do that under very special circumstances. But for the most part, no. These guys, they just want electrons. Exactly. That all it needs is 1 more. Anytime it comes near a box of Kleenexes, it's like, ooh, give me that. That's what I need. Does that make sense? Super reactive. Now, do you remember that there were 2 properties that you learned in the last unit that were talking about electrons? The first one was talking about how much energy it took to make something an ion, ionization energy. You remember this? Chlorine, very high or very low? High on the right-hand side, right? The right-hand side of the table is very high ionization energy, right? Whereas the guys on the other side, very easy to give away these electrons. These guys over here, very hard. Do you remember this from your test just yesterday? Good. Okay. The other thing was called electronegativity. Remember what electronegativity means?
Yep.
How easily it attracts.
It attracts what? Electrons. And which ones were the most attractive? Top right, which would be chlorine and fluorine, right? And oxygen. These are the supermodels, right? It's not a matter of me having to steal these tissues, these electrons from Josh. The tissues are like, oh, wow, there's Mr. Hess. Oh, I want to go with him. I'm going to leave with Josh. I'm going with Mr. Hess. Because I am attractive to those tissues. I don't know what that means, but... Does that make sense? It's tough. But remember, he's happy, though. Because he's got his remaining electrons. He doesn't need this one. Right, absolutely. Okay. Are you with me, my friends? Okay, let's continue. How about sulfur?
The same thing.
Neon? 3s2, 3p4. Good. So I ask you, sir, quickly. How many electrons will this thing need to gain? 2, right? It's got 6, 2 and 4. So it needs 2 more to get to 8. Yes, sir. Exactly, because you're adding electrons. Electrons have a negative charge. So when I add these negatives, it gives me a negative. Check this out. Shh, last one. You guys are getting this, but I want to make sure we get through this all. For phosphorus.
Neon.
Would be neon. Nicely done, Evelyn. 3s2. 3p. 3. Nicely done. How many valence electrons for phosphorus? 5 valence electrons. How many does it need to be happy? 3 more. So therefore, what's its charge going to be? -3. Make sense? Let me show you a summary. For groups 1, 2, and 13, 15, 16, 17. For group 1, what charge are all those group 1 elements going to have? Positive, how many? 1, because they give away their 1 electron. Again, ignore hydrogen. Hydrogen is the funky one. How about group 2? What's its charge going to be? +2. Give away its 2 valence electrons. Group 13, +3. Remember we said the group number tells you the number of valence electrons. It also tells you the number of charge, right? How about on the other side? For group 17, what's the charge going to be? Not -7. Because -1, it needs to take just 1 more electron, right? To be happy. Group 16, -2, it needs 2 more. It has 6, it needs 2. And group 15, -3. These are something you can just know on your periodic table. If you see group 17, it has a -1 charge. If you're seeing group 2, it has a +2 charge. If it's making an ionic compound. Yes, ma'am.
What if you get
Good. We are not going to talk about those yet. We will, I promise. But just not yet, because they don't follow these nice, pretty, beautiful rules. Remember, they're those transition elements. Yes, ma'am? The metalloids are, again, funky. Sometimes they'll be like metals. Sometimes they'll be like non-metals. So we tend to ignore them right now. Okay? Again, these are all very good questions. Sir?
So do the elements in group 14 bond with other elements in group 14?
Cool. So you notice, by the way, that we're missing group 14 here, right? You notice that? Here's the reason. Look at group 14 on your periodic table. Do you see what a funky mix group 14 is? Look at it. You've got carbon, which is like the non-metallist of non-metals. Okay? All of the life that we know is based on carbon, right? Super covalent bond maker. Okay? That's the first one in group 14. Then you get two metalloids. You get silicon and germanium, which are like the metalloids of, they're like super metalloids, right? I mean, silicon is what we make all of our computer stuff on, right? It can be like a metal, but it's not like a metal. And then you've got these two metals on the bottom, tin and lead, which are very metally. So this is like just the funky group. Okay? Periodicity does not apply to group 14. Okay? It just doesn't. They're too different. So they're put together based upon their number of valence electrons. So we ignore them. You can make ionic compounds with tin and lead. We'll talk about them because they act like transition elements. Okay, so a perfect question. What else are we missing up here? There's two other things that are missing.
18.
Group 18. Why isn't group 18 here? They're noble gases, so who cares? What does that mean? They already have 8. Right? They don't need to react. They're so cool, everybody wants to be like them. Right? I don't need to react with you, Ryan. I already got my 8. Right? And the other thing we're missing is groups 3 through 12. Again, there's the D block Raleigh mentioned before. And again, we'll talk about those. They have some special rules. Sir? So theoretically, not theoretically, we can make noble gases react. Neon, argon, krypton, xenon, radon. If you put them under enough pressure and enough heat, you can get them to share their electrons. Very rare. They don't like to do that. And helium, we can't make react at all. No matter what we've done, we can't make it happen. It's too unreactive. The other guys, if you really squish them and make them super hot, you can make them react with fluorine. Are you with me, friends? Fantastic. All right, I'm going to stop the video now.